Where did we leave off? We were talking about quadrature. So let's recall the last time. We proved the quadrature of all rectilinear shapes, if I'm not mistaken. Proved the quadrature of all rectilinear shapes. The simpler terminology for rectilinear shapes is polygons. But rectilinear, i.e. polygons, rectilinear refers to the fact that the sides are all straight lines. Allison.
For like proving the quadrature of a triangle.
Yes.
For that, with the same thing, like we use the exact same proof if you're using a square.
Yeah, let's. So it's true that a square is a rectangle. If our goal is to, quadrature means to turn something into a square with the same area. So if you already started with a square, there's nothing to do. You've already created a square with the same area as the square that you were given. But let's go over this, because some of these proofs, they seem magical. Like, how would you come up with this construction? So now that we've seen the construction, and for the rectangle, we've seen it twice in a row, let's see how you could have discovered that, because that's the other thing I want you to get a feel for. Like, how did people come up with this stuff? So how could you have discovered, how could you, and I really mean you, have discovered let's make your life better, these constructions on your own? Okay, so that's an important thing to be able to think about. So let's go back to the rectangle. So what you're really trying to do, if you have a length A and you have a length B, whoops, that's supposed to be a B. If you're given a rectangle like this, you need to construct AB. You need to construct something with area AB. Want area A times B. So side length, that's the square. Want a square with that area. So side length, square root of AB, right? This we're clear on. And here's the thing that you might notice when you're playing around with stuff. So notice, this is just the kind of thing mathematicians do. They play around. They don't necessarily have a goal in mind. They're just observing things, finding patterns, and then realizing that those patterns have consequences. So here's one pattern that we might notice. If I take A plus B quantity squared, hopefully we all remember that that's A squared plus 2AB plus B squared. No mystery there, just doing out the algebra. Again, this isn't how the ancients would have understood these things. We have the benefit of thousands of years of mathematicians working out algebra and being able to write things in this compact form. But let's use it since we have it. We might also notice that if we replace the plus sign by a minus sign, the A squared stays the same. All the changes is that instead of a plus 2AB, we'll get a minus 2AB. And that both of these things are squares, which is interesting from the viewpoint of the Pythagorean theorem, especially since what we're trying to do is take a square root. And so if I subtract, I'm going to negate this. Negate, negate, negate. I'm just multiplying both sides by -1 because I want to subtract the top row from the bottom row. Now I can just add since I negated the bottom row. Addition is just, subtraction is just addition of the negative. So on this side, I would get A plus B squared minus A minus B squared. And on this side, the A squareds cancel, the B squareds cancel, and all I'm left with is 4AB. So that's almost what I want. I want A times B, except I've got 4 of them. So if I divide by 4, so divide both sides by 4, I would now dividing by 4 inside a square is the same thing as dividing by 2 outside the square is the same thing as dividing by 2 inside the square. So this is a plus b over 2 squared minus a minus b over 2 squared, because 2 squared is 4, is equal to ab. This is the key identity. Once you realize this key identity, okay, so let's rewrite this identity. I'm just going to move the, I'm going to think of the AB as square root of AB quantity squared. And now it really smells like a Pythagorean theorem. Because if I move this to the other side, I get that A plus B over 2 quantity squared is equal to this A minus B over 2 quantity squared plus root AB quantity squared. Did anyone follow any of this algebra? Anna, take me back.
Could you go over what happens underneath, divide both sides by 4?
Yes. So if I divide this side by 4, I just get AB. If I divide this side by 4, I get a quarter A plus B squared minus a quarter A minus B squared. And that 1/4 outside the square is the same thing as a half inside the square. Yeah. Sorry, I went over that a little fast. Alexandra. Yeah, that's a great question. Yeah, that's a great question. That's a great question. So the pattern that I wanted to see is that the A plus B squared is almost the same thing as an A minus B squared. It's just that we get a plus 2AB, here we get a minus 2AB. And so if what we're looking for is an A times B, when we subtract one from the other, the A's are gone and the B's are gone. So it was just, I went over that a little too quickly as well. It's just that I saw the AB in the middle with other stuff, but I could get rid of the other stuff by subtracting. That's the key insight there. Layla.
Why did we do this to be?
We're trying to see how we could discover a construction of the rectangle. Last time I just gave you the construction, and then we verified that the construction works. And the question is, how could you discover the construction on your own? What if you're in the middle of a midterm and you forgot? You're like, oh no, I don't remember. There's like some complicated moves, right? You have to like draw a circle here and there. How are you going to remember what's going on? I don't remember anything. I really don't. You know, there's like a couple of cool things that I know are involved. And those are the only things that I have to hold on to in order to construct everything else. And so the one cool thing that I notice is that A plus B and A minus B, when you square them, you get almost the same thing, except there's a different sign inside the A times B term, the 2AB. Here it comes with a plus sign, there with a minus sign. So if I subtract, I'll get rid of everything except the AB. Now I don't get AB, I get 4AB, so fine, I have to divide by 4. And then you just do a little bit of algebra to clear everything apart from the AB. The AB, the reason I want AB is because it's root AB squared. And then we pretty quickly derive an equation like this. And now, once you have an equation like this, the construction almost writes itself. So let's go back to the construction. You've got an A over here. You've got a B over there. What you're trying to make is an A plus, you need a right triangle with hypotenuse, A plus B over 2, and one of the sides, A minus B over 2. Then the last side will be root AB. That's what the Pythagorean theorem is telling us. Actually, the converse of the Pythagorean theorem is that if this relationship is satisfied, then we have a right triangle. Does that make sense? So how are we going to do it? Well, if I extend, so this length was A, this length was B. If I extend A by a length B, then this total will be A plus B. That's a little too much. I want half of that. So if I cut it in half somewhere here, then this will be A plus B over 2. And by the way, this was adding B to the length of A. A was this original length. That original length is A. I added B to that length, and then I cut that length in half. That already makes my, whoops, A plus B over 2. Missing some parentheses there. Okay, so that's one of the lengths that I want, but I want that to be the hypotenuse. So if I draw a right triangle and I draw a circle here, then I'd bring that length to the hypotenuse. I'm working backwards now. This isn't really the construction. You can't just do this. You have to actually construct it, but how could you find the construction? So if I drop a right angle here, then now I've drawn a hypotenuse with length a plus b over 2. What's this length? Well, if this much was a plus b, a half a plus a half b, and I subtract a b off of it, this much is a minus b over 2. And now we're done, because this is the length that we want, this root AB, by the Pythagorean theorem. Okay, so if you, on the exam, you forget what the construction was, if you just think, how am I going to make an a plus b over 2? How am I going to make an a minus b over 2 to get this root AB? The construction tells you, I mean, the algebra tells you how to do it. You had this length b over here. You'll draw a little semicircle over there. You'll extend this. That gets you that extra length. You cut it in half. You draw this circle to bring the hypotenuse from the side down, and then you're done. Jemima and then Lily.
No, sorry, I'm just generally confused. I don't have like a specific question. Why? Okay, wait. Why is the hypotenuse of the triangle a plus b?
Well, if we're trying to match this pattern says if I have one side length, which is a minus b over 2 squared, and another side length, which is root ab squared, then the hypotenuse will be a plus b over 2 squared.
Put it in the triangle.
Yeah, we want to engineer that equation geometrically.
I was just confused because I understood why when you split it in half, and you got that length, that
Yep.
was a plus b over 2.
Yep.
I was with you until then.
Okay. So I want to bring this a plus b over 2. Let me give this a little color. I want to bring this a plus b over 2 to the hypotenuse of a right triangle. And so if I draw a circle centered at this point with this radius, then it's also the radius. Yes, exactly. Exactly. Awesome. Thank you for that question, because I'm guaranteed that there are 5 other people who, that's not what I wanted. Okay. Who were confused about that. So that's what this little arc is meant to represent. That's a radius. Little.
And the other side of the triangle, the smaller one? why is
Yes.
it
Okay, very good. Let's go over that. So why is this part a minus b over 2? Because this is the halfway point. So from here to this new point is also this big length. This big length is a half a plus a half b. In other words, it's a plus b over 2, just like this length is also a plus b over 2. So when I subtract b from there to get the red, so the red length is this length, a over 2 plus b over 2 minus a whole b, because I'm taking b away just to get the red. And so if you have a half a, that stays, plus a half b minus a whole b, negative b over 2. Yeah, so a over 2 minus b over 2, which is a minus b all over 2. Yeah, thanks for that question. Okay, I just wanted to give you like some ideas about how you could have come up with this on your own if you hadn't, it wasn't shown to you originally. All right, so we have the quadrature of the rectangle. Any questions on that? Could you come up with this if you needed to, if you forgot? Okay, we've got the quadrature of the rectangle. From that we had, so quadrature of the rectangle gave us the quadrature of the triangle, because if you have a triangle, let me do it like this. You can drop a perpendicular, and you can take half of that perpendicular, this is the halfway point, and then you can draw a rectangle. I'm just trying to illustrate a situation that we didn't face last time, which is when the altitude is outside the triangle. You could have chosen a different altitude. Doesn't matter. I'm just reminding you. So the area of a triangle is 1/2 base times height. And base times height is, of course, exactly what you do with a rectangle. So once you've drawn this rectangle, which is pretty easy to draw, then then we know that rectangles by this complicated process are quadruple. So are triangles. This is all still review. And from that, we managed to get any polygon, then any, I'll still say rectilinear because I want to make rectilinear shape. A polygon is quadruple. Quadruple. By the way, most people say squareable. I like quadruple better. It's a weird word. Why? Because if I have any shape whatsoever, there's one more idea here, by the way. If I have any shape whatsoever, so 2 steps, 2 ideas. Idea 1 is if you have any shape, you can, Danny, break it into triangles, triangulate. So step 1 is cut it into triangles, exactly right. And okay, each triangle is quadruple. And how do you add areas? So idea 2 is add areas of squares. In other words, given 2 squares, construct a square that has an area which is the sum of those 2. So if I have a square with area A and another square, I gave it away, with area B, how are you going to construct a square with area A plus B? The Pythagorean theorem. That's exactly what the Pythagorean theorem is for. This C, sorry. So C is equal to A plus B as areas. Okay, so the addition of areas of squares is exactly the Pythagorean theorem. Okay, and that's where we left off last time. Is that right? Mark. Very good. Excellent question. What if you have more than 2 squares? So you've taken your squares A and B and added to make square C. So now you have this square C, but now you have another square you want to add on to that. You just keep doing it. Yep. If you have another square D you want to add on, now you make a new square with area E, where E is C plus D. If you can add 2 things, then you can add a third and a fourth, as long as there's only finitely many. So that's what these rectilinear shapes are. Excellent question. Thank you for that. I was waiting for that, for someone to notice that we only did one iteration, but you can continue the iteration. Okay, so here's our first great theorem. Maybe I'm overselling this. Like, this is a big bang, but I hope you also appreciate how big a bang this is. And more than the theorem is the discussion the theorem leads to, which is where we're headed. So this is the great theorem is the Hippocratic Hippocrates's, let's say, not to be confused with the oath, Hippocrates's quadrature of the Lune. Okay. Ta-da. Great theorem. Okay. What's the construction? So the setup. We start with a right isosceles triangle. You notice the entire, I don't know how many weeks we are into the lectures. We have 4 weeks, thank you, into the lectures. We have not left this object. This object continues to give us new things to play with. And this is the beauty of mathematics, is the more you play with something, sometimes, not always, but the more interesting things there are to learn from this. So let's start with right isosceles triangle. We've already learned so much from this object. We started here with YBC 7289. We've been milking this thing for a long time. Let's call this A, B, and C. So this is maybe step, I don't know, step 0. or something. Let's just call it step 1. Step 2 is draw a semicircle on BC. Okay, so I'm going to draw a semicircle on BC. I'm going to use BC as the diameter of a semicircle. Now, where will that pass, inside of A or outside of A? Which is outside or inside of A? I try to draw a semicircle here. I could do it on the other side. Yeah, there's a reason I want to draw it on this side. Very good. I didn't specify which side. I want to draw a semicircle on the same side as A. And the question is, what will happen? Josie? Why?
The triangle that has one side of the diameter of the circle.
Yes. Yes. It's actually the converse of Thales's theorem. If you have a right triangle and you draw, Thales's theorem says if you have a diameter of a semicircle or a circle or whatever, and A is a point on the circle, then the angle there is right. The converse, this is the converse to Thales's theorem. If you have a right angle, then semicircle on the diameter, semicircle on this diameter passes through that point, goes through that point. Okay. You see why that's the opposite direction. Thales's theorem says if you have a point A that's on the circle, then the angle is right. The converse is if the angle is right, then when you try to draw that circle, or just half of it, it will pass through that point. So it doesn't go inside A, it doesn't go outside A, it goes right through A. So far, so good? Okay. And step 3 is to draw a semicircle on AB. So I have here AB. I'm going to draw a semicircle on AB. Let's give these curves names just so I can refer to them. I'll say this curve is E, and I'll say this curve is D, just to keep A, B, C, D, E. And his great theorem, his great theorem is if you go from A to D to B and back along E, what shape do you get? A lune. Looks like a moon. Lune is another word for moon, right? This is a lune. This lune is quadruple. Okay, this shape, unlike the rectilinear shapes we've been studying, this is a curvilinear shape. This is curvilinear. It's bounded by arcs of circles, segments of circles, by arcs of circles, instead of being bounded by rectilinear is bounded by straight lines. Okay, that's what the word curvilinear means. It's not a shape that's bounded by circles. Sorry.
D and E referring to the areas or to the lines?
To the lines. D and E are lines. Maybe if some color will help clarify that. So this is D, and is this a good color, or is this not going to show up? That's not a good color. Let's go with green. That's not a great color either. Is that coming through at all? Does that make sense? So I just wanted D to be able to refer to that curve. D and E are curves. Leah.
Line E is part of the line.
Yes. In fact, E, we can think of this whole thing as E, if you like. E is what we drew in step 2. Yeah, let's call that curve E. And what we drew in step 3 is the curve D. Okay. So far, so good. Everybody understand why? So why do we have a right to be able to construct a square that has exactly the same area as this funny rectilinear shape, as this lune. That's what Hippocrates is telling us. All right, so why? The proof uses, his proof uses the following fact, that the area of a semicircle divided by the area of the square on that diameter, of the corresponding square on its diameter, that this is constant. Constant. Okay, so if I draw a semicircle, this is area A, and I draw a square that has the side length of that semicircle, and I make that B, or I draw some other semicircle, some larger semicircle with area C and a square on that with area D, what this fact is saying, so this fact says that area of A divided by area of B is the same as area C divided by area D. Yeah, it doesn't matter what size it was. When you divide the area of the semicircle by the area of the square on the diameter of the semicircle, these will be in proportion. Okay, area of C divided by area of D. Now, there's some dispute about among historians about whether Hippocrates actually could prove this fact. It is proved in Euclid's Elements, so I'll just make a little note. Note dispute among historians on whether Hippocrates really knew how to prove this fact. It does appear with proof in Euclid's Elements, but there's argument about whether the proof that's given in Hippocrates's Elements and his construction of the Lune is valid. Please.
Be able to show us this on the fancy technology.
Yes. Why is this fact true? Let's see why, in modern terms, let's see why this fact is true.
That would show us though by.
Yeah, the GeoGebra thing. You want a nicer picture of the Lune.
Like, I want the numbers, like.
Oh, the numbers. Yes. Let's do it algebraically, and you'll see that you don't actually need the numbers. Okay. In modern terms, what's the area of a circle? Pi r squared. Everybody knows pi r squared. So the area of a semicircle, yeah, a half pi r squared, exactly right. And now, what's the diameter of a circle in terms of the radius? These are all in terms of r. R is the radius. 2r. Diameter is just twice the radius. So what's the area of the square on the diameter? Exactly. It's 2r quantity squared, also known as 4 times r squared. And so I'm looking for the ratio of these two things. The area of the semicircle divided by the area of the square on the diameter. So area of semicircle divided by area of the square. Take a minute and make sure you work out what that is. Give me a thumbs up when you got it. Kind of. So the area of the semicircle is this 1/2 pi r squared. The area of the square is this 4 r squared. And what do we notice? Exactly. The r squareds cancel out. You're left with whatever this is, pi over 8 or something. And this is a constant. Does not matter what the radius was. So Lisa, does that satisfy you? I could probably figure out how to divide things and make a semicircle and in GeoGebra, but maybe this is even more convincing. That this constant is the same value regardless what the radius of the semicircle was. Yes. Yes, I didn't say the time. Oh, thank you for that reminder. When was this roughly? Does anybody remember? 600 is Thales. Hippocrates is after the Pythagoreans, which are 550 BC. Yeah, it turns out he's more like 450, 400. Let's call it 450 to 400 BC. Yes, at the time. Very good question. Very, very good question. We're going to have a whole long extended discussion about pi itself. So let me save my answer for that. But even this, okay, we're going to have a whole discussion about Archimedes. And when we talk about Archimedes, we're going to talk a lot about pi because he's like the person that made pi a thing. So just let me answer that question in like 2 weeks or something. 4 weeks at the pace I'm going. Yeah. Lisha.
I've shown those two numbers are constant. It's not just shown that A, B, and C, D are the same.
Yes. Yeah, exactly right. Because if I take the area of AB divided the area of A divided by the area of B, here I'll get pi over 8. Whereas here, if I take the area of A divided by B, what I'll get is, oh, also pi over 8. And so regardless of how big A and C were, when you make the squares on those semicircles, the ratios are universal. There's one constant. They would not have known this constant to be pi over 8. Not until Archimedes. But they would know that whatever it is, it's some constant. All that's saying is the areas of circles grow quadratically. That's what they know. They have a funny way of saying it. Because they don't speak about things having quadratic growth. Okay, so far so good. We're almost up to, okay, so given this one fact, which again, people doubt whether Hippocrates had a proof of that fact, but he certainly knew that fact because he used it in his proof. But whether he could establish it himself, we don't know. Please.
Is there a way to make a square to a circle to then do this rather than doing a rectangle to a square?
So what I think what's way easier is to understand this relationship in modern terms. And what I was showing you is what that relationship looks like in their world, which is this kind of thing. They don't have pi over 8. So what they can say is if you make one semicircle and a square on the diameter of that semicircle, and you make another semicircle and a square on the diameter of that semicircle, their areas will be in proportion.
Then let's make a rectangle. Now make a circle around B. Now make a circle around.
That is
A
not.
plus B over 2.
That's not saying. So what you're describing is the quadrature of something. That's not saying that the shape A is quadruple. This square does not have the same area as this semicircle. The ratio of the areas is some constant, but I don't know how to shrink the square by the right amount so that I'll make a square with exactly the same area as the semicircle. Okay, so let's distinguish. It's a very, very good question. Let's distinguish between the quadrature of this semicircle, which is not what we're talking about at the moment. We're talking about the quadrature of the lune, of this ABDE lune shape. But you're asking a very insightful question, which is, why are we doing anything? We could just constructed a square. The area of the square is not the same as the area of the semicircle. In fact, I can put the square right on top of the semicircle, and then you'll see very easily that they're nowhere near, right? Pi over pi is like 3, so it's like 3/8. The area of A is like 3/8 the area of B. But the proportion that this area fills up of the square is the same as the proportion as the bigger area fills up of the bigger square. This is also about 3/8. Does that make sense?
Can I find a square that's the same size as A?
We're gonna come, okay, you're asking very, very good questions. Wait like 20 minutes and we're gonna come to that question. Okay, that's called squaring the circle. Trying to find a square that has, determining whether the circle is quadruple or not. That's a very deep question, one that we will come to, I hope today, but we're not ready for it just yet, if that's okay. Great question. Other questions? Are we ready for the proof of this, the quadrature of the Hippocrates Lune? Yeah? Okay, let's do it. So I'll just redraw it here so that we have the picture again. So we had this isosceles right triangle, A, B, C. We drew, I think in green, the semicircle on BC, which passes through A because there's a right triangle here. And then we drew a semicircle on AB that we called D. This one we called E. I'll just say E down here, but it's also E over here. And then this is the shape that we're interested in. Okay, so here's the key idea. Let's look, the key idea, proof. Look at the area of, well, before we do areas, this is a right triangle. He knows the Pythagorean theorem. So what do I know about AB squared plus AC squared? Is BC squared. Okay, BC squared. So that's a square on the length of AB. By the way, AC is the same as, it's the same as AB. It's an isosceles right triangle. So this is 2AB squared is equal to BC squared, which let me just divide by 2 on both sides. So a square on AB has half the area as a square on BC. That's just the Pythagorean theorem. Is everybody happy with that? But that means that the area of the semicircle, so semicircle, the semicircle that goes from, let's go A to B along D, A to B to D. That's the semicircle on AB. I claim that that's also half of the area of the semicircle on BC. In other words, BC and then E. BCE. Do you buy that? That's exactly using the principle that the squares, AB squared is the area of the square on AB relative to the area of the semicircle. And that'll be the same as the square on BC relative to that semicircle. And if these were in a 2-to-1 ratio, then these are also in a 2-to-1 ratio. Does everybody follow that? Okay. I want to visualize this half of the area of the semicircle. So I'm going to cut the semicircle in half. Let's mark a point here. So the only bit of the construction is bisect BC. Bisect BC at O. O because it's the center of a circle. I like calling centers O. And draw AO. Draw AO. Okay, so I'm just going to drop this perpendicular here. So far, so good. The area of this quarter circle from B to O to A and then back along E is exactly half of the area of the big semicircle from B to C and then along E. I just cut it in half. Everybody see that? The whole purpose of constructing O was so I can visualize this half of the area. So this is the area of going from B. This is a quarter circle. Quarter circle going from B to O to A and then back along E. Is everybody with me on that? I don't know how to shade this without ruining everything. It's this bit in here. Who's with me? Who sees what I'm pointing to? Who's against me? Who? Yeah. So what I'm saying is this half of the area of the semicircle from B to C and then along E, I just cut it in half and I get a quarter circle from B to O to A and then along E. Okay. Everybody see that? So look at what we've shown. Let me try so again, what we've shown is that the area, if I go from B down to A and then over along D, that area, that's what this area was, is the same as the quarter circle area, which goes from B over to O, down to A, and then along E to the other side. Those two areas we just showed are the same. Lori.
How did you get the semicircle ABD? The Lune rather ABD is this half.
We're not up to the Lune yet.
What is ABD?
ABD is you go from A up to B and then to D. So this is the semicircle, not the Lune. Yep. So the Lune, by the way, the Lune would be right about here. If I were to cut this here, I would get the Lune. Or if I were to draw D there, I would get the Lune.
How did you get the ABD is half the?
So if you take the semicircle A to B to D, and you compare that to the semicircle B to C to E,
The radius is half.
the radius is, well, the radius is changed by a factor of square root of 2. So the area is changed by a factor of 2. That's exactly this pi over 8 argument. They're in the same proportion. So if the square on AB is half as big as a square on BC, then a semicircle on ABD is half the semicircle on BCE. Does that clarify things? Everybody's with me? So check this out. If I want to get the Lune, what do I have to subtract from the semicircle ABD? ABE. There's this E that I would need to take out. What would happen if I took out ABE from here?
Which one is E on
E is this semicircle.
on the bottom, sorry.
On the bottom, E is this. This is E. Yeah, let's keep the color coding. No, E is just I'm calling anything along this line E. The green is called E. Okay, but we don't have to travel the whole length of it. If we're going from A along D to B and then along E back to A, then we stop there. Is that okay? Or do you want me to call this something else? Like F or something? No, it's okay. It makes sense. Thank you. Eleanor. Yes. Yes, exactly right. So here's what Eleanor is saying. Okay, well, we just showed, let's just one more time. We have that the area of the semicircle from A to B to D, or B to A to D, I don't know how you want to label these, bad, the semicircle BAD, which includes this little bit from A to B to E, is the same as the area of the quarter circle from B to O to A and then back to B along E. And what Eleanor is saying is subtract off the area from A to B to E, A to B to E, from both sides. Area from A to B to E. So if I take A to B to E and I subtract it from the quarter circle, what's left? Eleanor. The triangle BOA. Does everybody see that? I'm just cutting off the top of the cone, the ice cream cone. On the other side, what's left? When I cut out the same ABE, the lune, what's left is the lune. Anyway, it's just the lune. So if we look back at our picture from the very beginning, this lune has exactly the same area. If I drop this perpendicular, has exactly the same area as this triangle. It's a bad drawing. Yeah, let's try. Let's try. I'm going to try to get a good drawing for you. Question. I thought I heard a question. No axes, no grid. We didn't have any of that stuff until Descartes. Okay, right triangle. Well, let's start with that and drop a perpendicular. Okay, and then let's make a circle from A to B so that it's isosceles. So now I have an isosceles right triangle. There's my point ABC. Did I get the labeling isn't the same? Is that okay? This B and C are flipped. All right, then we're going to draw this line. We'll bisect this line. Let's get a midpoint between B and C. This we would call O. Here it's called D, unfortunately. And then let's draw our first semicircle, which, by the way, hits A. Remember that? Let me hide this circle so that it's not in, don't show this object. Okay, that's our first, that's the semicircle that we were calling E, this arc. And then, again, let me bisect B and C, or A and C, rather, so that I can draw a circle here. And this is our lune. I have no idea how to have it compute the area of a lune. No, it's not going to give me the area of this lune. But let me drop the triangle, and maybe this picture is more convincing. So this area from let's make a polygon, which is from here to here to here to there. That area, this area, is the area of the lune. What is this? Go away. This area, that triangle, has the same area as the lune. Isn't that crazy? It doesn't even look right. It looks bigger. What if I draw the lune? You can kind of see the lune on the other side. Yeah, Layla?
Is this thing in the book where it was like, it only works like 3 times?
Yes, we're getting to that. Yeah, we're coming to that, Layla. Elitsa. Yes.
Or if you do it on the other side, which is saying before, then you double that triangle, now you square.
Yes.
And then you're able to see what you're missing.
Yes.
Well, then you can also, but you're also able to envision what's missing, meaning, A1 plus C1 plus C1 plus B, like whatever those are on the other side, are the same as the inside of the.
So this square, the question, there's the inscribed square, inscribe the circle. The problem is,
Now, everything that's on the outside.
Yeah.
That those outsides
yeah,
can have a relationship with,
with the square.
no, but also with the inside, which is the same as the square.
Keep playing with this. I love that you're asking these questions. I'm going to show you in a minute that I think what you're suggesting is an attempt to square the circle. And when we get to the 3 impossible constructions of the ancients, you'll see that that's not possible. So keep playing. I don't want to stop you, but I want to move on. So let's talk after. Because this is exactly what I'm hoping is going to happen, is that you guys can't help yourselves, but start asking questions. Because that's what Hippocrates did. He couldn't help himself, but start poking around, and he discovered this incredible fact. Amelia. Okay. Do you want to ask it anyway, even though you know the answer?
No. I was just wondering
Yeah.
if if you could rearrange it in some way to make the right triangle or make the Lune with the right, but
Yeah. Let me try to draw the Lune on the other side if I can, so that you can see the Lune and the right triangle together. Actually, it's easier to draw the right triangle on the other side. So let's in fact,
I found it easier for you to say what I'm trying to say.
please.
Okay. So if we said that that triangle equals the outside, moon. That
Yeah.
means that what's left, so the other ones is equals the inside.
Yes. In other words, so the Lune is this moon-looking thing, and what we're cutting out from the triangle is equal to these two shapes, has equal area to these two shapes. Yeah. So there's some amount that's, yeah.
I don't know, but that.
Yeah.
So the minimal way, now we just proved that that's true.
Yes. Yes. That the area of this thing is the same as the area of these two little white bits left over. Okay. The amount that's outside the Lune is the same as the amount that's inside the Lune, that's missing from the triangle. Weird. Okay.
That could help you there. Anyway, if you wanted to make additional drawings, now you're able to, then you could calculate what's the triangle, if you wanted to have a hat that's not a triangle, but you wanted to subtract the inside Lune to save as the two on the outside. So you wanted.
Yeah. Yeah. So this shape is the same as those, but that doesn't.
Triangle minus that shape.
I understand. So, yes. So there's this like curvy linear it has two lines and one circular arc boundary. That shape is not necessarily quadruple. In fact, I believe it. I haven't done the calculation, but I think it's not. Almost none of the Lunes are quadruple. Almost any picture that you can draw like this cannot be related to a square or a rectilinear shape. What's incredible, and this is, let's come back to the theorem. What have we just proved? We proved that the Lune has the same area as a triangle. So what? Triangles are quadruple. But triangles, so just to finish it, but triangles are quadruple. And hence, so is the Quod erat demonstratum. Just to finish that. Yes. You're finding all kinds of other cool patterns.
Now that we have more options of things that are quadruple, it'll be easier for us to figure out what that is.
Potentially. So here's what happens next. Let me just continue the story. Here's what happens next. Supposedly, and this is a big, there are a lot of times, I'm a mathematician, I'm not a historian. I hope that is probably abundantly clear by now. And there are times when I read things that historians write about mathematics, and I just say, I can't help but notice that what this person is writing is being written by someone who has never proved a theorem. Like, you would not be saying this if you have proved a theorem in your life. If you've discovered something independently, what you're describing, what some historical things that I read, I just immediately zero in on the fact that no mathematician would hypothesize that this is what's going on. So I don't know. I don't know what happens, but supposedly there's discussion from 500 years after Hippocrates. We're talking like 100 or 200 AD now, Common Era. Supposedly, Hippocrates then claimed that he could square the circle. Square the circle. So let me very quickly show you how supposedly he claimed to do that. Again, it seems to me that Hippocrates is a little too smart to fall into this trap, but let me show you what the trap is just so that you're aware of it. Okay, so claim the circle is also quadruple. The circle itself is quadruple. The circle is quadruple, and here's the proof. Construct a regular hexagon. So you take an equilateral triangle. So construct regular hexagon. So I'm going to take this equilateral triangle. I'll put another one over here. I'll put another one over here. I'll put another one over here and over here and over here, and I get a regular hexagon. Okay, 6 equilateral triangles. We have no problem constructing equilateral triangles. We can do all of this. Let's say we have the length AB. So this is the length AB. Okay, so this is maybe step 1. Step 2 is construct a semicircle. Well, first let's call this center O. Let's draw a circle with center O and radius AO. In other words, inscribe the hexagon in a circle. This is surprisingly hard to do. Okay, there's our circle that has the hexagon inscribed. And step 3 is draw a semicircle on the diameter AB. So on AB, we'll draw this semicircle. And 5 more, and 5 more. Continue this sort of flower arrangement. So there's another one, there's another semicircle, there's another semicircle, there's another semicircle, there's another semicircle. So far, so good? Now let's look at the total area. Look at the total area. Okay, from 2 different vantage points. One vantage point is that we have the circle on O, the big circle. So it's either the big circle plus we have all these lunes, right? These little lunes. So there's a big circle on O, and then how many lunes, Lori? Sorry. The radius of the small semicircles is half BA. So I'm using BA as a diameter. Yep. So radius is 1/2 AB. So when I say a semicircle on AB, I'm using AB as a diameter. Great question. Okay, so we have this big circle at O, plus these lunes, and how many of these lunes are there? 6, it's a hexagon. There's 6 of them, plus 6 lunes. That's one way to describe the total area. Another way is to say, well, we have this hexagon plus 6 semicircles, right? We could take the hexagon plus the semicircles. Here, let me draw one of these semicircles a little bit better. And how many of those semicircles are there? 6. Hexagon plus 6 small semicircles. Is everybody happy with this equal sign? Those 2 shapes are the same. Now, what's the relationship between the radius of the big circle versus the radius of the little circle? Exactly, because the radius of the big circle is AB or AO, because these are all the same because we have equilateral triangles. Okay, so the big circle, so what's the area of the big circle? So radius of big circle is twice radius of the little circle, well, semicircle. So the area of the big circle is how many areas of the little circles? guess. Remember, Hippocrates used the fact that areas of semicircles or circles, same thing, grow quadratically. So if you double the radius, the area increases by a factor of 4. The area is 4 times the area of the little circle. Little circle. Does everybody see that? This big circle has twice the radius and hence 4 times the area. So let's continue the calculation. So instead of big circle here, I'll put 4 times the area of a little circle, but a whole circle, plus these 6 lunes. On the other side, I have a hexagon, plus 6 small semicircles. 6 semicircles is the same as, you can glue 2 halves of circles together to make a whole, is Danny? 3 little circles, 3 areas of little circles. The little circles are the circles on AB, with AB as the diameter. Does everybody see that? So what we're doing here is taking, grouping these semicircles and putting 2 halves together to make a full circle, and we can do that 3 times as we go around the 6 semicircles. So now we've got 6, or 3 rather, little circles glued together from 6 semicircles. Over here, the big area is 4 little circles, because it has twice the radius, plus the 6 lunes. Anything we can subtract from both sides? 3 times the area of the little circle, we can subtract from both sides. That means that the area of the little circle, meaning the circle on AB as its diameter, is equal to the hexagon minus 6 lunes. This is all correct. There's nothing wrong with any of this. You follow that? Elitsa, where did I lose you? I subtracted 3 little circles from both sides. Instead of 4 little circles, now I just have 1. And then I simultaneously, maybe I'm doing too much at once. I simultaneously move the 6 lunes to the other side with a minus. Okay. The hexagon, what do we know about the hexagon? It's quadruple because it's rectilinear. It's rectilinear, so this is quadruple. How about the lunes? We just said lunes are quadruple. So we've just squared the circle. We've constructed a way of making a square whose area is the same as the area of a circle. Amelia. Exactly right. Okay, we didn't fool Amelia. And I don't think Hippocrates was fooled by this either. I don't know why historians say he would fall for this. What Amelia is saying is, wait a second. We didn't say lunes in general are quadruple. We had one particular lune, the one that came from an isosceles right triangle. That lune, we did prove the quadrature of. This lune is a completely different lune. We did not verify that this one was quadruple. And in fact, it can't be, because as we'll see in a second, that neither is the circle. Okay, so the faulty argument would be, therefore, circles are quadruple. And no, they're not. Okay, so that's why this is a claim. And the claim is, I should say, now that we've seen it, it's a false claim. Okay, like I said, generating ideas is really important. Ideas are good, then you have to evaluate those ideas to determine which of them work and which ones don't work, and make sure you discard the ones that don't work. Josie. Please, of the original Hippocratic lune? Yes? Yes.
somehow figure that out.
So this line right here. Okay, great. So this was BAD. That's the semicircle on AB. ABD, if I take this semicircle. On the other side, I claim that that's half the area of the big semicircle from BC and then running along E. Why? The reason is that the square on AB is half of the square on BC. And squares are to areas of semicircles on those diameters. Now let's recurse back. Why is this true? Why is it true that the square on AB is half the square on BC? And that's the Pythagorean theorem. The fact that we have an isosceles right triangle. BAC is the isosceles right triangle that we started with. Yes. Josie, did that answer your question? Okay. Come back after. Let's look at it again. Okay. So does everyone see why this faulty argument could have been attributed to Hippocrates? Sorry, historians, I just don't believe it. Hippocrates was too smart to make this mistake. Amelia saw it immediately, right? Wait a second, that's a different Lune. That's not the Lune we were dealing. Yeah, to answer the story with Lunes, so this is kind of great. Hippocrates did find, so let's write some words. Hippocrates did find two other lunes that really were quadruple. Not this one, meaning not the one above that we just discussed. And that's where things sat until Leonard Euler in 1771. Yes, in 1771, found two more. And then finally in the 20th century, Chebotarev, who was the other guy? I wrote it down. Dorodnov, I think, proved that these 5 lunes really are the only ones that are quadruple. This mathematics is outside the scope of what we can do in this class. But if you want to read up on these things, I just want to plant those seeds in your head. Okay, we have 2 minutes. Before we go, let me tell you they're the big 3. These are the big 3 problems. Big 3 problems of construction problems of antiquity. Construction problems of antiquity. Okay, one is trisecting an angle. Let me write them down, and then we'll be able to talk about them starting next time. Trisecting an angle. 2 is doubling a cube. Doubling a cube. And 3 is the big one. It's what we've been talking about, squaring a circle. People were trying to figure out, is it possible to solve any of these problems with straight edge and compass? And they worked really, really hard for about 2,000 years. And so should I give away the punchline? Punchline. What's the punchline? How many of these are actually solvable with straight edge and compass? 0. None of these. None are solvable. The resolution, the fact that we know for a fact, we have theorems that say certain things cannot be done. That's an incredible thing if you think about it for a second. You think, well, we're not smart enough to come up with some algorithm by which you can square a circle. No, it can't ever be done.
So when you say they're not possible with straight edge and compass, that means like totally at all?
Totally at all. How is that provable? How can you possibly prove something like that? So this is attributed to Wansel. Wansel proves 1 and 2. This is like 1837-ish. And anybody know who proved that circles can't be squared? This is a famous among mathematicians theorem. So 3 is due to Ferdinand Lindemann in 1880. I'm gonna make up a number. 5. Why not? Halfway. I won't be off by too much. I don't remember the exact number, the exact year. Okay, so we're going to talk about squaring the circle and also about this. And I'll just give you a hint as to how such a thing could possibly be proved, because it seems crazy that it's within the realm of possibility.